So this is lecture 14, May 5th, 2021. Okay. And this is week 6. Hard to believe that time is flying by. So we are still covering the topic of harmonic excitation of damped systems. Okay, so let me very quickly summarize where we are. We looked at the excitation of a force subjected to a simple harmonic load, whether, of course, can be this form or this form, okay? And we introduced the frequency response function. So frequency response function is that quantity that amplifies the corresponding static displacement, or if the system is subjected to a constant force of F naught, you want to find the maximum dynamic displacement if this force is applied cyclically. That's what frequency response function is, and we study that in detail. Then based on that concept, we also looked at rotating unbalance that introduces a also different form of sinusoidal or the harmonic excitation, and basically is the same, that except that F naught here is this, simply this. So this is F naught times sine omega t, and the equivalent of, I would say, frequency response function was this, right? And we compared these two, what happens in the case of simple harmonic, or when you have an unbalanced, unbalance causing the displacement. The frequency response functions were quite different. In this case, you had this peak value of frequency response function shifting to the left, depending, of course, on the damping ratio. In this case, and start at the 1 at r equal to 0, the value is 1. Here at r equal to 0, they start at 0. And in fact, you see a shift of frequency, a shift of the amplitude towards right of r equal to 1. We discussed all of these. So just to refresh your memory, because we are going to get back to these. These are the frequency response function is something that you will be using it when we get to, especially multi-degree of freedom systems. You see that we'll explore these further. But let's move on, and I will introduce a new topic, although this is not necessarily related only to harmonic excitation, but we will look at it in the few cases where the harmonic excitation is involved, and then we will see the importance of this topic. So time-dependent input displacement. I kind of briefly started that last time. As I said, let's consider that you have a system supported by a structure, okay? And let's say this may be even moving, then for a variety of reasons, In other words, this u with respect to its own base. Now, the support of the structure gets subjected to a displacement. So the absolute displacement of this mass would be z, where z is u plus y. So, and u is the relative displacement. So we derive the equation of motion when the system is subjected to an input displacement by setting up the free body diagram. So if this is moving, the forcing uh, is generated in the damper and the uh, spring, and putting the lumbar force in the opposite direction of motion, we derive the equation of motion to be what? mz double dot plus cu dot plus ku is equal to 0, where f of k is, of course, ku, and f of c is cu dot. But since um, z is y plus u, if you substitute that into that equation, okay, you find it leads to this form of the equation, which is my plus u double dot plus cu dot plus ku is equal to 0, or simplifying this, because mu double dot plus cu dot plus ku is equal to negative my double dot. So if you want to, this is the relative displacement of the structure with respect to its base, okay, where that is subjected to an input displacement. The right-hand side, which is the forcing function, would be the mass times the input acceleration. This is the form that is of interest in structural engineering or structural dynamics or earthquake engineering, when you have, for instance, earthquake records that are given in terms of the acceleration data. So that's how you can find displacement of the structure. But if you're more interested in absolute displacement, okay, so you need to convert the relative displacement into that absolute displacement. So you substitute this into that equation. So the equation becomes mz double dot plus c z dot, if after you simplify it, plus kz is equal to cy dot plus ky. So the absolute displacement of the system can be found from this equation of motion, where the right hand side is simply the due to the displacement caused in this spring and the velocity in this damper due to this input displacement. Okay, so bear this in mind. We are going to get back to this in the general case, but before going over the general case, let me do some simple problem, at least to show you some simple application of this. And this is my favorite example. Let's say you have um, a road which is a rough road, and the roughness is sinusoidal. In other words, let's say all these roughnesses you have in a road, okay, change as this, sinusoidal function. So let's say one cycle of this road has a length of L. Okay, all these bumps you see in the road, they repeat themselves. The shape is, the behavior is sinusoidal. So the cycle is of length L. So a car is traveling on this road. let's say, is traveling in this direction. So this is the road, okay? A car is traveling. So let's consider the car being undamped. So it consists, can be modeled as a mass and a stiffness. The stiffness is all the stiffness components from the suspension system to tire and whatnot. So this is the car, is traveling in this direction. And we assume that this car is traveling at a constant velocity, okay? And the height of this, or depth of whatever, of this road, uh, you know, roughness, let's say this, if this is y, this is y, um, y is given with this function, y sine of 2 pi x over L, okay? Where y is the maximum amplitude of this roughness, okay? So if this is the function describing the roughness of the road, okay, what we want, and this is a, uh, a car, the travel, the distance traveled by car, we want to find the most undesirable speed of this car. So in other words, we want to find, okay, at what speed, um, what is the speed we should avoid, given that you have an input function, right, which has a frequency. So given that the system that we have, the car, is undamped, the equation of motion with respect to that absolute display, in terms of that absolute displacement, which we wrote, would be like this, right? Cy dot plus ky. Since the system is undamped, the equation of motion would be taking this simple form, okay? So given the equation for y, we substitute for that, you have this sine of 2 pi x over L, and x is given, x is basically the distance at any point where the car is, and car travels as distance with a constant velocity. So substituting for this as vt, the right hand side becomes ky times sine of 2 pi v over L times t. So you can see the right hand side is a sinusoidal function. This is the frequency, okay, due to this road, rough road. So the equation of motion is simply this, is ky sine 2 pi over L, okay, v
Professor?
t. Yes,
So x equals vt, right?
correct, yes.
Um, oh, okay, sorry. So the v and the t are both inside the sign. You just wrote it like that to
Yes, yes, yes,
okay, gotcha.
yes,
Yeah. Okay.
yes, that's right.
All right,
But
thank
what I
you.
said was, this is, if you think of it as this sinusoidal function, this would be the frequency, right?
Yep.
So given this equation of motion, we want to find the most undesirable speed. So what is the natural frequency of this system? It's simply k over m. What is the frequency of this oscillation due to this input displacement? Omega is 2 pi v over L. So The most undesirable speed would be, given that the system is undamped, when you have resonance. The frequency of the system or natural frequency becomes equal to the frequency of the excitation. So let's just equate those two, which, of course, given that this is a function of that velocity, we can find that velocity to be L over 2 pi k over m. So the velocity that we should avoid is simply related to the length of the one cycle of this road's roughness divided by 2 pi times the natural frequency of the system. So now that you have learned this, you can go to your friends who have not taken the course in vibration and you tell them, you know what? Let's assume that the road roughness on California Avenue is sinusoidal. So I'm going to advise you what speed you should avoid when you're driving on that road so you don't feel dizzy. And of course, your friend is going to laugh at you, say he's really crazy. How in the world a road can be, roughness can be sinusoidal? You say, I'm an engineer. Engineers make assumptions and approximations to deal with real world problems. Okay. And then you derive this and giving him this advice. Find out what is the stiffness in your car for all the support systems. You have the mass of your car. So don't ever, never travel with that speed. Otherwise, you get dizzy. Anyway, so any questions? This was a simple, of course, problem. So let's do another example. Okay. So this is another example. Let's say we have a sensitive equipment that is uh, maybe buried underground. So you have a damping system um, on the top and the below that and supporting this sensitive equipment, which is this mass. But then, for whatever reasons, the top surface, let's say this is buried underground, is experiences some displacement, and you want to find out what happens to the sensitive equipment. Okay, for instance, find out how much how much uh, displacement this would experience. Would that exceed the displacement, that the threshold that this equipment was designed for, not to exceed that? So let me kind of redo this, redraw this. This is what you have. You have basically a mass, right? Supported by, let's say, this stiffness and a damper. And on the other side, you have another damper, right? C2. And this is the ground motion, okay? And so you want to find out basically what maximum displacement this system experiences if it is subjected to a displacement like this. So let's introduce some. These are the two things we want to find out. What is the equation of motion? That's the first thing we need to do. And then find the maximum displacement that this mass experiences. So let's make this problem a little bit meaningful. So let me give you some values here, some simple values for these parameters. Let's say mass is 1, k is 1, let's say unit is all in English units, so whatever these are. Damping ratio of the system is given, and the input displacement, let's say, is a sinusoidal function that looks like this. Okay. So with those information given, let's solve the problem. We want to find the maximum displacement. So as the first step, we need to derive the equation of motion. And our concern is the maximum displacement that this mass experiences, right? Or the relative displacement. So the equation of motion can be easily found by setting up the free body diagram, assuming y is greater than u. So on this end, you have this force of k, which would be k u, f of c, which would be c1 u dot. On the other side, this damper would experience a force that fc2, where fc2 would be what? Would be c2 times the velocity that this experiences, which would be y minus u dot. And of course, you have the lumbar force in this direction, mu double dot. So from this free body diagram, you can easily set up the equation of motion. So let's write that down. You have mu double dot plus c1 u dot plus ku minus c2 y dot minus u dot, right? So this is equal to 0. Simplify that, becomes mu
Professor,
double dot.
I have a question on your setup.
Sure.
How did you know the lumbar force was pointing to the left and not the right?
See, I'm assuming that the motion is in this direction. So the
Okay,
lumbar force is always in the opposite direction of motion.
thank you.
Does that answer? Oh, you're welcome. So let me simplify this. You have C1 plus C2 u dot, and then plus Ku is C2y dot. So this is the equation of motion. So now, where of course y is given, the function for the y. Since the values are given in terms of the damping ratio, I will convert this to the alternative form of the equation of motion. You remember we had u double dot plus 2 zeta omega n u dot plus omega n squared u. That was the left-hand side. If you had some f on the other side, you just divide it by m. That's what the left-hand side would look like. So let's write that equation in terms of these quantities. First of all, omega n is k over m. K is given 1, m is 1, so that's 1 radians per second. Okay. Zeta is given 0.2, that quantity. And m is given, C2 was given. So I would substitute for all those values in this equation, and you will have what? You have u double dot plus 2 times zeta, which is 0.2 times omega n 1, u dot plus omega n, which is 1. So this would be just u is equal to C2 times y. Okay, C2 is given as 2. Y is y dot. Y was 0.1 sine omega t. Omega was 1. So y dot is simply 0.1 omega cosine omega t. So that would be y dot. So right-hand side would be just 0.1 times cosine omega t or cosine t. Okay, so that's the right-hand side. Let me further simplify that more. So you have u double dot plus 0.4 u dot plus u is equal to 0.2 cosine t. So this is your f naught cosine omega t, right? This is 1, f2 is 0.2, okay? So this is the equation of motion. If you want to find u max is what?
Professor, I have a
You
question real
have-
fast.
Sure.
How'd you get from C1 plus C2 to 0.4? I'm just a little confused that
Okay.
steps there.
C1, okay, plus C2. C2 was given as 2, right? When I converted this to this form, okay, I ended up with zeta. Zeta is already given, okay? So I converted this equation to this form since zeta is given, okay? So I don't worry about C1 plus C2 because that converts to divided by m would be just 2 zeta omega n, okay? So I don't need to worry about what C2 is, okay? Does that answer the question?
Yeah,
I mean,
thank you.
sure. So, because you're only given C2, right? But not C1. But instead of C1, you're given basically the combination of these divided by m, which is zeta, okay? Or 2 zeta omega n. So U max is simply F0 over K times H, right? So F0 over K is what? F naught is 0.2, K is 1, so this is simply 0.2. All I need is to find H. And for this case of a system subjected to a harmonic load, right? What do I have? Okay, I have H is 1 over 1 minus R squared plus 4 zeta squared R squared. Okay, and so let me put that value in. Okay, F naught over K, let me write that down again, was 0.2. Okay, H is going to be 1 over 1 minus 1. R is 1, right? Because omega is 1, omega n was 1, so R is 1, plus 4 times zeta, 0.2 squared times R is 1. So H is simply 1 over 2 times 0.2 or 1 over 0.4. So U max then would be what? 1 over 0.4, right? Which is H times F0 over K, which is 0.2. So it would be simply 0.5 inches. So if you're concerned about that sensitive equipment and you want to find the maximum displacement that it experiences, that's how you find it. Okay. So this was another example.
Again?
I'm sorry.
What is the original Umax equation?
You remember if you have equation of motion, right? Mu double dot plus Cu dot plus Ku is equal to F naught sine omega t, right?
Yeah.
We said that H is what? Is,
Frequency response.
right? So the maximum response is always static response times H, right? That's how we find Umax. This is H, this is F0 over K. Does it answer the question?
Yeah.
Professor,
Yes.
when would we use like H star like that version?
Oh, that's the rotating unbalance.
Okay.
Yeah, this is just this simple harmonic load. Okay. Yeah, that's only for the case of rotating unbalanced systems. Any other questions? All right. So let's go and go over another example. All right. So now you have a system like this. Okay. K1, C1. So you have a mass supported by these two stiffnesses and dampers, okay? And this end is connected to a rigid, massless plate, okay? And this massless plate experiences some input displacement. And the form of this input displacement happen to be a sinusoidal function of this form. So let me also give these quantities again, these parameters that are given in the problem. Let's say C1 is 2 pound/second per inch. C2 is half of C1. K1 is 100 pounds per inch, and K2 is half of K1. Mass is given as 10 pounds. Okay. These are all the information given, and what this problem is asking for is this. First, given the input displacement, we want to derive the equation of motion. We also want to find, okay, what is the natural frequency and the damping ratio in that system, of the given system. Okay, and then we want to find or derive an expression for the maximum displacement that this mass experiences over the amplitude of the input displacement. So let's say you are designing this system and you're concerned about, again, let's say this is a sensitive equipment, and you want to find the relative value of the maximum displacement that this mass experiences with respect to the amplitude of the input displacement, so that you kind of set up a table that, okay, if the input displacement has such and such amplitude, this would be you can quickly find the maximum displacement that this mass experiences. So it's kind of a generalized form of the previous problem that I gave you, okay? So you want to find this quantity as a function of given parameters, that is of the system, C1, C2, K1, K2, M, omega, and basically omega n. So you want to find an expression for this, okay? And of course, you're doing that because you want to find out, okay, for instance, the value of this ratio when you experience the severe case, the forcing frequency is equal to the natural frequency of the system, assuming, of course, again, that y is greater than u. Okay, any question as far as the statement goes?
What does the line over the y mean in part C?
What is this you say? This is
The
the
line
amplitude.
over the.
Oh, the
You know
line
how it
over
has
it?
a line over it? Yeah.
Yeah, well, that's what it means. I just put a bar
Oh, okay. Thank you.
for the amplitude. Sorry, that I did not put it here. Yeah, that's the amplitude of the input displacement. Any other questions? All right, so let's start first by deriving the equation of motion. Again, we can do that by simply setting up the free body diagram. This mass is moving in this direction. So this spring and this damper will be subjected to a force that is generated to do the relative displacement of these. So these are the forces on the left side. K2 and C2 would be subjected to a displacement, which is y, relative displacement, y minus u. So the restoring force on this side would be y minus u. The damping force would be C2 times y minus u dot. And again, assuming that the system is moving in that direction, this is the relative displacement. So the mass would experience this inertial force converted to the lumbar force in this way. So this is the free body diagram. That is, now by writing summation of force along x equal to 0, I can set up the equation of motion. So let's add up all these forces. You have m u double dot minus k2 times u minus y minus u, okay? Then you have C2 times u dot minus y dot plus K1 u plus C1 u dot is equal to 0. So all the forces added up. First, simplify this, becomes mu double dot plus C1 plus C2 u dot and plus K1 plus K2 u is equal to taking this term and this term to the other side. So you have K2y plus C2y dot. So this is the equation of motion. Okay. Any questions? All right. So
Quick question. Could
Can
you
you
go over
expand
why you
on that?
have K2 and C2, those forces going to the right?
why there? Because if this is, we're assuming that y is greater than u. Okay. So in other words, this plate is being stretched by y. Okay. But u is being, and of course, this is moving at the same time. So what displacement K2 experiences? The difference of y and u, right? Think about this spring, this is at the spring. this end is moving u, this end is moving y, right? So
Oh,
this
okay.
is,
Yeah.
so that K2 experiences y minus u. Same thing with that damper. This end is subject to the displacement u, this end is subject to displacement y. So relative displacement would be, okay. Any other questions? All right, so let's now put those values, parameters, for these parameters that I have. But again, before doing that, since in the second part, the problem is asking for zeta and omega n, I'm going to convert this to the alternative form. That means I divide this by m, the whole equation by m. So this becomes u double dot plus 1/2 C1 plus C2 u dot plus 1 over m K1 plus K2 u, and the right-hand side becomes 1 over m K2 y plus C2 y dot. So I just converted that form to this form. And why is that? Because I know now this is 2 zeta omega n, and this is omega n squared. Okay, so let's substitute now those values for these parameters. Okay,
I have a quick question.
sure, please.
At the bottom of the page on the right, where you have 1 over m multiplied by k, what's the subscript on that k?
Oh, that's K2. That was K2
Okay,
times y.
thanks.
Sure, same equation that I had, just divided by 1 over n. Any other questions? All right.
Yeah, on the C1 plus C2, the
Mhm.
coefficient for that, it's 1/2,
It's 1/2.
right?
Right.
Why is there not an m in the denominator?
So I divided by, wait a minute, how much was mass? Oh, this is not 1 over 2, this is 1 over 10. For some reason, I thought mass was 2. Sorry about that. That's good observation.
So
Okay.
should the others be 10 as well?
This would be 10. For some reason, I put this in here. Oh, no. Wait a minute. C1 plus C2, okay? C2 was half of C1, okay? Okay, so let me keep this as 1m. Sorry about that. Let's keep this all, not my mistake. That was not 1 over 2. That was 1 over m. Okay, so I'm glad you noticed that. It was 1 over m. Any other questions? So I don't know why I wrote 1 over 2. So let me rewrite this because we need it on this side. I need that. So let me rewrite that equation. I have u double dot plus 1 over m C1 plus C2 u dot plus 1 over m K1 plus K2 u, okay? And then I have 1 over m K2y plus C2y dot. So this is the equation. As I said, this is 2 zeta omega n. This is going to be omega n squared, right? Is that clear? Why? Or no question? Okay, so now let's substitute those values. I have u double dot plus 1 over 10. C1 was 2, and C2 was half of that. So this is that, plus 1 over 10. K1 was 100, K2 was half of that, okay? And this is 1 over 10. K2 was half of K1, and C2 was half of C1, which was 1. So it's just simply Y dot. So let's further simplify this. You get Y double dot plus 0.3 U dot plus 15 U is equal to 0.1 times 50 Y plus Y double dot. Okay, so this is your f of t. We'll get to that. And this is the left-hand side. So for part, so far, this was what we did was part A. Part B is asking you to find natural frequency and the damping ratio. So you look at this equation. This is 2 zeta omega n. This is omega n squared. So omega n squared is 15. That means omega n comes out to be 3.873 radians per second. So 2 zeta omega n, 3.873, is equal to 0.3, right? So from here, zeta comes out to be 0.3 divided by 2 times 3.873, or 0.039, or zeta is almost 4%. Okay? Any questions? All right. One more part. Actually, two more. You want to find U max with respect to Y, where Y is given as Y sine omega t. Okay? So the right-hand side, which is f of t, is what? F of t is 0.1 times 50 times this, y sine omega t, and y dot, which is obviously derivative of this, y dot would be y omega cosine omega t, right? So it would be then y omega cosine omega t. Okay, so the equation of motion then, which you had here, is this: plus 0.15 u is equal to 0.1 y. I write it like this. 0.1 actually would be 0.1 y times 50. So it would be 5y sine omega t plus 0.1 y w cosine omega t. Why did I separate these two? Because what you have on the right-hand side is the sum of two sinusoidal functions. You remember from strength of material or wherever, right? That if you have a system subjected to separate loadings, as long as the displacement is small, you can use the concept of superposition, right? If I want to find U, right? Or for that matter, U max, I can find the U max due to this forcing function, and the total U mass would be due to that. Remember, let's say in the strength of material, you had a beam with these two loads, F1 and F2, and you wanted to find the displacement in the middle, delta. What do? You can find the displacement in the middle due to this force, delta 1, find the displacement in the middle to do this force, F2. So total delta was delta 1 plus delta 2, principle of superposition. Okay? So I'm not going to obviously be able to finish this problem, but let me at least guide you to help you to find that. So if I want to find U max, okay, which is F0 over K times H, I need to do this for both of these. So U1 max would be what? Would be 5y divided by K, right, times H. U2 max would be what? 0.1y divided by K times H. Okay? Problem is asking you to find U max as a ratio of the U max over Y. Okay? U max is, I would factor Y out. Okay? Y actually over K out. So you have 5H plus 0.1H. Okay? So you can easily find the ratio of U max over Y, which would be just simply a function of H and K. I'm going to stop here because you know what, of course, what H is. H is 1 over square root of 1 minus R squared plus 4 zeta squared R squared. Okay, so you can substitute for H given these values. You have K, which is total stiffness of the system, and you can find that. So I did not get a chance to finish this problem, but in fact, next time we are going to actually do this problem in the general form of it and by introducing a concept, which is what we are going to, in fact, discuss as the next topic. But let me stop right here. Okay. Any questions? If not, I will see you either during my office hours or on Wednesday.